Hi everybody, I'm the greatest living inventor, and today we are doing my invention, unspinning hurricanes. Let me write it down. Unspinning. Oh, you know what? I bought new markers. So this is the time for a new marker. Unspinning hurricanes. Okay, so I will try to do it faster. I recorded it already, and it took me about 1 hour and 45 minutes, so I need to do it a lot faster, so I'll just read to you and draw when it's applicable. Okay, so 1 second. I will take off my shirt. Okay. Okay. Stopping tropical cyclone storms. Okay, the general name for hurricanes is cyclones. Okay. Also known as hurricanes or typhoons. If it's in the upper, in the northern hemisphere of the Earth, it's called hurricane. If it's in the lower, if in the southern hemisphere, it's called typhoon. Okay, so typhoon, cyclone. It's all the same, but this one is spinning counterclockwise, and this one is spinning clockwise. Okay. Stopping tropical cyclone storms, also known as hurricane typhoon, early when they start to form by interfering with the chain of events that created them. In 2012, Popular Science published an article called "To Stop a Hurricane, Shoot It Full of Dry Ice" by Rose Pastore. Okay, I will put links to everything in the description. In 2017, the National Geographic published an article called "Can We Engineer a Way to Stop a Hurricane?" by Cynthia Barnett. They explained about Project Stormfury, and earlier attempts and their inconclusive results, meaning sometimes it worked, sometimes it didn't work, didn't stop the hurricane. And about later ideas of cooling the warm seas that energize these storms. I invented some different ideas that I will now present. In parentheses, one is close to Project Cirrus. Okay, so one is close to Project Cirrus, but more focused, in quotes. Close parentheses. arranged by order of fail-safe protections that back up one another. Meaning, if one fails, we try the next one. If that fails, we try the next one, and so on. Okay, so I'm raising and writing each time my next step, the next part of my invention. Okay, so this part is called wind traps. Although the name is taken from my favorite sci-fi novel, Dune, the idea is different. In the book, they are catching humidity from the air. Okay. In addition to saving lives and property in the United States, these wind traps will produce a lot of electricity, which will cover some of the costs of running them. I read this article. Most hurricanes that hit the US start in the exact same location. That's the name of the article. In ScienceAlert by Fiona MacDonald. According to her, the hurricanes that hit the USA are made by the African easterly jet. African easterly jet. Okay, it's a name of a stream of winds. I'm not sure how reliable is that website, ScienceAlert, so I'm relying on Wikipedia. This jet maximum wind speeds are at a height of 3 kilometers. Okay, so if this is the ground, this is the ground, we are somewhere in Africa, and the wind blows this is the wind. Let's put it in light blue. Okay, so okay, this is the wind, and the height of this is 3 kilometers. The jet's maximum wind speed is at the height of 3 kilometers. How do we harvest this wind? The first step is to take a huge funnel, make a huge funnel. The entry of the funnel will reach the desired height of 3 kilometers. So ideally, we would build, we cannot do this, but I'm saying ideally, we would build a big funnel, okay, a funnel which takes all the wind. But we cannot do this because we cannot build so high. Unfortunately, the first step is to make a huge funnel. The entry of the funnel will reach the desired height of 3 kilometers. Unfortunately, we cannot build buildings that high, so we will build the structure like a huge fly tent with a very large entry and very small exit. Normally the fabric, okay, like a tent that you make in the woods. Normally the fabric is held by a pole, stick. But in our case, it will be anchored to a helicopter that will hover in the same place at the 3 kilometers height. Okay, so here we have a helicopter. And okay, this is supposed to be a helicopter, and it holds a fabric, something like a cloth, a big cloth that we can make as big as we want. So it's 3 kilometers. Okay, it's let's say one helicopter here and one helicopter there, and they hold the cloth spread. A helicopter can hover in 3.169 kilometers, so a little bit more than 3 kilometers, so that's okay. As soon as it runs low on fuel, again. To have constant uptime, we arrange 2 wind traps, one behind the other. Okay, so we have one solution is we can make another one like this, and the wind, if this one lands and refuels, the wind reaches the other one, and vice versa. When this one lands, this one is active. And another solution is that we can hook the same cloth, like if it has some hook, and then raise another helicopter from the ground, and then this one takes over. Okay, this one holds, and this one lands and refuels, and alternately. Okay, so either we use another cloth, another wind trap, or another 2 helicopters. By the way, instead of one strong helicopter, we can use a few small drones for the same task, and they can be powered with solar power, charged by day, fly by night. The fabric itself should be the same material which is used for parachutes. Strong, light, durable to weather, and of course able to handle strong wind. What will be in the exit of this funnel? Okay, so we have the funnel, and what will be here? We will build wind turbines that look like a long tunnel with a few propellers, one behind the other. Okay, so we have like propellers, and like more propellers, and this is a tunnel. Okay, and when the wind comes out, it's already weak. Okay, because we took all the energy to run the turbines, to rotate the propellers. Sorry. Okay, when the wind goes out, it's already weak because we took all the energy to rotate the propellers. Okay, we will build wind turbines that look like a long tunnel with a few propellers, one behind the other. The end of the tunnel is open, so the air can come out, but now it's much slower. Okay, now the next part of my invention, which is called proto-cyclones. Proto-cyclones. Okay, let's see how we're doing with the time. 15 minutes, okay. Here is a quote from a paper named The Formation of Tropical Cyclones by David J. Raymond from New Mexico Tech. The only source that I was able to find was Dr. Joanne Simpson, Mesoscale Interactions in Tropical Cyclone Genesis. Protocyclones first develop a vortex. Protocyclones first develop a vortex is an eddy, at middle levels in the troposphere, in the certain layer of the atmosphere. Only then does a smaller surface vortex, a smaller eddy, form beneath the mid-level vortex. Okay, so first it forms the big vortex in the troposphere, in the middle of the troposphere, and then, only then, one forms below. A smaller one. According to Wikipedia, the altitude of the troposphere in the tropics is 18 kilometers. Okay, so here, if we had these 3 kilometers, now it's we need 18 kilometers, which is a lot more. Normally, drones can only reach 3 kilometers high, but an unmanned gas balloon can reach 50 kilometers. Okay, so if we had an unmanned gas balloon like a Zeppelin, this could reach 50 kilometers. So what we do, we combine, okay, this is like a propeller. So what we do is we combine the two. So if we'll connect a drone to one or more balloons, I think we can get it to fly and navigate by GPS at the required altitude of 18 kilometers. What will be the most effective thing for the... Okay, so we take a drone. So this gives him the navigation, and this gives him the... It's tied to a balloon, and the balloon gives it the lift. So it can, if the balloon can reach 50 kilometers, it can reach with the drone 18 kilometers. And then the drone navigates with the propellers. So if we'll connect the drone to one or more balloons, I think we can get it to fly and navigate by GPS at the required altitude of 18 kilometers. What will be the most effective thing for the drones to do there? To answer this, we need to understand what the wind is doing there, which is a ring. Okay, so the wind in this troposphere. This is the troposphere. And the wind, the African jet, eastern jet, is making a ring. It comes like this and goes around to make a ring. Here is a very nice video about Coriolis Force by Eric Snodgrass. Okay, so I'm putting the link, but just it's so important that you will see it that I'm putting the name also. I'm writing the name. Coriolis Force. And the video is by Eric Snodgrass. Okay, so it's really important that you'll see the video. I will put a link in the description. A short video explaining the Coriolis effect starring several graduate students from the Department of Atmospheric Science at the University of Illinois Urbana-Champaign. Watch what happens on minute 441. When Amanda, the African wind, is pushing the baseball, the air, on the rotating merry-go-round, planet Earth, in a straight line. But the baseball, the air, is getting back to her in a circle, ring of air. Okay, so there is a part in the video which I really recommend that you see. This is a merry-go-round from above, and it's rotating. And the girl is sitting here. Okay, and she's throwing a ball. And she's rolling it in this direction, but the ball is making a movement in a circle. Okay, it's coming back to her because of the rotation. It's really impressive. So you should see it. This ring of air, when it closes and forces itself, gains independence and eventually descends down and sits on the ocean. Okay, this is down here is the ocean. Sits on the ocean like a torus or a bagel of rotating air. Okay, torus is this shape like a bagel, like a donut. Okay, we need the drones to disperse or redirect the air from the African wind, ideally before it closes a loop, or at least before it gains strength. Since we need to locate this phenomena first through satellite images, okay, we use satellites. This is crucial to the we cannot see it from a ship. We need to see it from above. Okay, so we have a satellite. And the satellite has a camera, and it sees the cyclone, and then it tells the drones which are on a ship nearby or in the area what to get to the air and start do their stuff. Since we need to locate this phenomena first through satellite images that will see the movement of the ring directly or maybe indirectly by following the African wind moving clouds. Okay, like if there is a cloud here and it's spotting that the cloud is all moving and suddenly it's moving slower, then it's also an indication. Because why slower? Because it's no longer going only here, it's going in other directions. Or maybe indirectly by following the African wind moving clouds and spotting places where there is a sudden decrease in the linear wind speed, because that's where the ring steals the energy to do its thing. At night we can do it by infrared, because I think that at night the hurricanes won't form that much, because the next stages require evaporation on the water surface, meaning sun's energy. Okay, so at night we have less heat. So how will the little drones redirect the ring, which can be a few kilometers in diameter? Okay, how can the drones redirect the ring? We can use the same trick we did before with the fabric tunnel. The drones will rise in closed formation with the fabric folded, and then will spread out themselves, and this will unfold the fabric in the sky and then maintain position. Okay, so we have the drones hold this fabric, and in each corner there is a drone with a balloon, and they spread out. Okay, so they have a lot of surface. The cloth, the fabric has a lot of surface. The drones are small, but the fabric is large. And then maintain position. It doesn't have to be nearly as big as the funnel we mentioned earlier. I think a few tenths of meters, a few dozen meters, will do in the diameter of the entry will suffice. Where will they direct the current? How do you position the fabric? The most important thing is to destroy the ring. Writing sounds like Lord of the Rings, haha. So I suggest outwards. Okay, so we direct it away from the ring. Okay, so outwards means if this is the ring, like that, then outward means towards you, okay, or towards the board. Like that, but it's not down, it's like towards you, okay? Or like that, which means into the board. We are looking on it from above. So I suggest outwards. In our outwards is our best bet, because it will disperse the ring. If we try to redirect the flow inwards, it can short circuit, can make a smaller ring, and create two rings, possibly even tighter and faster. If we try to redirect it downward, this is towards you, this is not downward. But if we try to redirect it downwards, we might hasten the descent of the whole ring, which is the ring's ultimate goal. So we probably don't want to do that. If we redirect the ring upward, it will eventually come back down. If we don't have the technology to control where we redirect the currents, then a few different random directions are our next best bet after the outward position, after the outward option above. So either outward or in random directions, either this or that. Note, after the hurricane is already formed on the water, there is a phenomena of eye inside an eye. Okay, eye inside an eye. See in Wikipedia Eyewall Replacement cycle. Eyewall Replacement cycle. Since this only happens when the hurricane is already pretty strong, I don't think we need to worry, but we should check it out, and it could tip the scales towards the different random directions option above. Okay, now the next part, which is called secondary circulation. Let's see how we are with the time. 31 minutes. Okay, we need to rush things up. Secondary circulation. Secondary circulation. Okay, so I'm hurrying up a bit, excuse me. This means in, up, out, and down. In, I will explain in a minute. In, up, out, and down. And going again to in. Okay. Here is a paragraph from Wikipedia about tropical cyclones. The three-dimensional wind field in a tropical cyclone can be separated into two components, a primary circulation and a secondary circulation. The primary circulation is the rotational part of the flow. It's what you've seen in light blue before, the light blue arrows, which goes like this. The primary circulation is the rotational part of the flow. It is purely circular. The secondary circulation is the overturning, in, up, out, and down. Okay, it's in, up, out towards you, and down. Okay, so it's like that. If the primary circulation is like this, the secondary circulation is in towards the board, up towards you, out, and down. Okay, so if this is the primary circulation, okay, I will draw it in another way. This is the primary. And the secondary looks like this. In, up, out, and down. Okay, or in this side, in, up, out, and down. Okay, this is both of these are the secondary circulation. The light blue is the primary circulation, like this. The green is the secondary circulation, like this, or like this. Okay. The secondary circulation is the overturning, in, up, out, and down part of the flow. It is in the radial and vertical directions. The primary circulation is large in magnitude, it's strong, dominating the surface wind field, and is responsible for the majority of the damage a storm causes, while the secondary circulation is slower, but governs the energetics of the storm. Okay, it fuels it. If you can't imagine it, think of a slinky toy spring and bring its two ends together. So it's a whole circle, like you have a table here, and you put the slinky, you take the slinky, and you put it, and you connect its ends. Okay, so it's a circle like this of a slinky. So it's a whole circle, not just half a circle, as it is normally is. If we trace our finger along the slinky, this is the primary circulation. But if we let a small ant walk on the circle, it will walk in and out, in and out, in and out, which is the secondary circulation. Okay, like this. Towards you, down, towards me, and up. This torus, bagel or donut shape, made by the secondary circulation, is what keeps the flow of the primary circulation inside it. Okay, this is inside the green ones. Inside it, focused and directed in a ring circle. Okay, it's like there are like the rings, like the hoops of the slinky. So these green things are like the hoops of the slinky. They are all around. And they hold the blue ones. It's like when you direct a plasma with magnetic fields. See Tokamak in Wikipedia. The to part comes from the word of for toroidal in Russian. Tokamak. Without this torus, the ring will disperse and die out. In Project Cirrus, an airplane dropped from above, crushed dry ice into the cloud along the rain bands of the hurricane. I think the inconclusive results were because you cannot aim accurately when throwing things from a plane. So sometimes by chance it reached the optimal location along the inside of the eye of the hurricane. Okay, this is the eye of the hurricane. Which is formed because of the green movement. So this, if you look from above, it's like this. But if you look from the side, it's like like a wall. And the wall, and all around is a wall. And this is the eye of the hurricane. So if you look from above, it's like a circle. I think the inconclusive results were because you cannot aim accurately when throwing things from a plane, so sometimes by pure chance it reached the optimal location along the inside of the eye of the hurricane next to the eye wall, and sometimes it didn't. Also, they tried to fight the storm when it was already very strong, and I recommend to tackle it when it's small and weak. Okay, how to target the exact location? I'm keeping the drawing because it's the same drawing. how to tackle the exact location. And remember, this is all at sea. Let's see, what's the time? 40 minutes. Okay, I'll try to do everything in 5 minutes. It's hard, so bear with me. If we send flying drones in the air, they will not be able to fly through the storm. My idea is to attack the hurricane from below with underwater drones, which are small robotic submarines with robotic arms. There are two types, ROV, remotely operated vehicle, which is manual, and AUV, autonomous underwater vehicle, which is automatic. Normally the ROV requires people close by, but we cannot risk the people, so we can use one underwater drone or more that will stand in the middle between the people and the working robot and function as radio repeater. Okay, if we have here a boat with people and they have a remote control, and the robot here will signal the robot that is here. Okay, and the robot that is here. Okay, this is talking to this, and this is talking to this, so we can work from a far away range. Sorry. The ROVs and AUVs will be deployed in a safe distance from the storm from fast power boats. And then the robots will get closer to the whirlpool of the storm from underwater and encircle it. Let's say for simplicity that we send 4 robots and they position themselves to the north, south, east and west of the whirlpool. Each robot will carry with it a payload of dry ice in the shape of a torus, a donut, tied with a rope to a closed lifting bag, a camel. Okay, the closed lifting bag is what you use in rescue from not so deep water, and you want to get to the surface of the water fast. So it's like a bag that has also connected to a gas tank. Okay, and the bag that when we open the gas tank, the bag inflates, okay, and becomes really big. All the gas from the tank inflates the bag quickly. So, and it's connected, this thing is connected to a bagel. This is a rope, and it's connected to a bagel-shaped torus of dry ice. Okay, this is dry ice. And this is a closed lifting bag. So each robot has one system like this attached to it, and each robot will carry with it a payload of dry ice in the shape of a torus, which is tied with a rope to a closed lifting bag, a Camel, that is designed for rapid deployment. It has a scuba cylinder mounted on the outside, which contains sufficient air to inflate the bag. So when the robot inflates and releases the buoy, this is we talk about this as the buoy, the inflating bag. The buoy lifts the robot and floats to the surface of the water with the dry ice hanging from it in the water. The dry ice is heavier than water. If we manage to release the floating bags so that they float just outside the storm, here, the dry ice weight will be swept inside by the whirlpool currents. And if the rope is long enough, not much longer than the width of the eye wall, this is the eye wall and this is the width of the eye wall, then the floating bag will be stuck outside. Okay, so we have the floating bag here on the surface of the water, and we have the bagel here. And they are connected along the eye wall. They are stuck here. Then the floating bag will be stuck outside and the dry ice will be stuck inside, both of them very close to the eye wall. At this point of time, the dry ice is cooling the water in the exact position that is important for maximum effect of stopping the secondary circulation. It cools the green thing. It prevents the green thing. If experiments will prove that there isn't enough surface area for the dry ice to cool the water, we can incorporate a more porous design with more holes than a torus, which only has one hole, to the dry ice block. As a last resort, we can attach in advance a small hand grenade with a long time fuse to the dry ice block that will allow the dry ice to reach the optimum position before it explodes. Of course, then we no longer hold it in position. There is nothing to hold anymore, and chances are we also ruined the floating bag. Okay, the next part. Okay, 48 minutes, I'll try to finish. Dragging to the equator. Okay, dragging to the equator. If all else fails, and this means now that the eye wall is strong now, okay, because it took us a lot of time to fail here and to fail there, and now the eye wall is like the walls are strong. It takes much time, and by this time it's strong. So we can use that to our advantage. When you read about the Coriolis effect in Wikipedia, it says the horizontal deflection effect is greater near the poles, okay, like the North Pole, the South Pole, since the effective rotation rate about a local vertical axis is largest there and decreases to 0 at the equator. If you are curious why, you can see a nice explanation in this video of Veritasium in minute 4. Okay, Veritasium. And in minute 4 of the video, and the video is called "Does Water Swirl the Other Way in the Southern Hemisphere?" I will put a link. A hurricane can never cross the equator or it will die. It will not have Coriolis force. Of course, it can start in the lower hemisphere of the Earth, and there it's usually called a cyclone, but then it cannot cross the equator to the northern hemisphere of the Earth. So we can apply the same trick there. So the trick is to use the same underwater robots we used previously, this time to deploy a big and massive torus. Okay, so if this doesn't work, then we deploy a big massive torus. Bagel or donut shaped, closed lifting bag. Okay, this is from this kind. It's a bag, but it's shaped like a torus. So it has we can tie it to a rope and then tie the rope to the boat. To a ship, more likely a ship, because it needs to be strong. That we release this time to deploy a big massive torus, bagel or donut shaped closed lifting bag, that we release from the right under the middle of the storm. It will have a strong cable attached to it that we will tie to a ship that will slowly drag the whole storm towards the equator until it dies out. The cable needs to be long enough as to not putting the risk not to be putting the ship at risk. The weight of the lifting bag will bring it to the bottom of the funnel of the whirlpool, but its buoyancy will not allow it to sink to the bottom of the sea and exit under the storm. So it's stuck at the tip of the storm. We are just slowly pulling the tip of the storm, and the whole storm will follow and come with us. Okay, so I hope it was clear. I know it's rushed up, but that's it. And thank you very much. I'll see you in my next invention. Thank you. Bye-bye.